Here we're going to talk about a logic circuit that performs these rules of binary addition, and the logic circuit's called a half adder. So to come up with the logic circuit that will perform these addition rules here, these single bit addition rules, we're going to put these rules into a truth table. And the way we're going to do that is we're going to assign the variable a to this row of bits and the variable b to this row of bits, and then here at the output in the result, the furthest to the right bit. And by the way, the furthest to the right bit is called the LSB, the least significant bit. I don't think I've mentioned that term in the video. You probably saw it in the reading. Okay, but least significant bit, that's the furthest to the right bit in a string of ones and zeros. Well, the LSB of the result we're going to label S. Okay, and then the next bit to the left of the least significant bit we're going to label C. Now, I know it's not absolutely necessary to put the zeros here, but just to explicitly show that C for these results is 0, we'll do that. Okay, so we've just assigned variables to the bits that make up these rules. So now we're going to make a truth table where A and B are going to be on the input side, okay, and the result is going to be the output C and S. Okay, so if A is B and, or excuse me, if A is 0 and B is 0, the result is 0, 0. If we have 0, 1, see, I'm just putting these rules into the truth table. We got 0, 1 here. If we have 1, 0, we have 0, 1. And then if we have 1, 1, we have 1, 0. Okay, so you see I just took those rules of single bit addition, I put them in a truth table. And now once I put the rules into the truth table, I can come up with the logic circuit in a simple small truth table like this by just looking at each output separately and comparing to how it relates to the inputs. So here if I just look at output C, you can see that output C is only a 1 when both inputs are 1. Well, if you remember from our previous discussion, and let's bring our summary of logic gates here, well, that's an AND gate, right? An AND gate will give you 1 out only when both inputs are 1, otherwise the output is 0. So what we can do is just take an AND gate and put inputs A and B, and we'll have output C. Alright, actually let me make this AND gate a little bit better here. Alright, now we do the same thing for output S. Well, output S is a 1 only when the inputs are different. When the inputs are the same, output S is 0. So if we come back to our summary of gates here, well, that's the exclusive OR, right? The exclusive OR will give you that relationship between the output and inputs. It'll give you a 1 out when the inputs are different and a 0 out when the inputs are the same. So if we now just take an exclusive OR, okay, and just bring B down and A down, right? Same inputs. Well, the output of that exclusive OR is going to be S. So you see this logic circuit of a single AND gate and a single exclusive OR gate gives you this truth table that came from these rules of single bit binary addition. So this logic circuit is doing mathematics. It's doing base 2 mathematics. Okay, it would perform all these rules that we have listed here that made up our truth table. Now, before we move on, let's count how many transistors we have. Well, remember, AND gate, that was the first gate that we looked at in our videos, and that had 3 transistors. And the exclusive OR, well, that's the compound gate that's made up of several basic gates, and it took 8 transistors. So a total of 11 transistors to make this half adder circuit. Now the reason why it's called a half adder is because this logic circuit, while useful, doesn't do quite everything you would like it to do. It doesn't perform all the rules of single bit addition, because you could have a situation like this, and in fact, you know, most useful addition involves multiple bits, okay, not just single bits. So, you know, as an example, you know, we may want to add two 4-bit binary numbers, you know, say a binary 6 and a binary 7. Okay, well, as hopefully you've been doing in the PDF, the PDF file that's on Polylearn that talks about binary math and the basics of base 2 numbers and also base 2 mathematics. Well, when you have multiple bit binary numbers, you add them column by column, just like you would a base 10 number. So you start with the least significant bit column and work your way all the way up to the most significant bit column, right, which is the furthest to the left column. So you see here 0 plus 1 is 1. Okay, and then 1 plus 1 is 0, and then this 1 here, and this is why it was labeled C, is the carry, would get carried to the next column. Alright, well look, when you go to add this column here, you're adding 3 bits. You're adding 1 plus 1 plus 1, which is 3, and in binary a 3 is 1, 1. Well, you cannot add 3 bits with a half adder. You can only add 2 bits because it only has 2 inputs. So you see a half adder cannot do any 3-bit addition. So when adding multiple bit numbers like these two 4-bit binary numbers, you wouldn't be able to use a half adder for this column here. Okay, it just wouldn't work because it doesn't have 3 inputs. It doesn't have the necessary inputs. So that's why it's called a half adder, because in multiple bit addition it doesn't quite do everything you would like it to do. Well, there's another adding circuit that's called a full adder that can add 3 bits, because as you'll see, a full adder has 3 inputs, and that's what we're going to talk about in the next video.